Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion. So I'm going to briefly review the topic. So consider that we have a general curve. Let me draw it like this. And at a certain point at the curve, you want to know what is the acceleration of a certain particle. That's represented here in black. Well, we can decompose the particle's acceleration into two components. So first, we can approximate the trajectory at that point by a circle. Okay, so at that point, the trajectory looks like a circular trajectory that has a certain radius of curvature r. And the acceleration can be decomposed into a centripetal acceleration and a tangential acceleration. The centripetal acceleration accounts for the change in direction of the velocity and is equal to v squared divided by r is the radius of curvature, and the tangential acceleration is equal to the derivative of the speed v with respect to time and accounts for changes in speed. Okay, so in this exercise, what we have is a block that has a mass m and is released from rest from point B here in the figure that has a height h relative to point A, and our goal is to show that the speed v of the block when it reaches point A is equal to the square root of 2 times g times h. G is gravity's acceleration here. And in order to do that, in order to show this, I'm going to draw the free body diagram on the block. So here we have the block. Okay. The forces that act on the block are the normal force from the surface that acts perpendicular to the surface and the gravitational force. Okay. And I'm going to define angle theta to be this angle here, that the direction that is parallel to the trajectory of the mass of the block makes with the horizontal. Okay, this is angle theta. Notice that this means that this angle here is theta as well. And I'm going to decompose the forces, and in particular the gravitational force, into two components. A component that is perpendicular to the surface and another one that is parallel to the surface. Okay, so in the component that's perpendicular to the surface, which I'm going to call R, we have, and actually let me draw it in the opposite direction, the R component, so that the R component is pointing, actually, I'm sorry, I'm going to draw in this direction, just as I had before. I'm sorry for that. So in the R direction, we have that the forces are N minus mg times cosine of theta, and this is equal to m times the acceleration in the r direction. This is just the centripetal acceleration, which is v squared divided by r. In the theta direction, we have mg times sine of theta, and this is equal to m times the tangential acceleration. Okay, so this means that the tangential acceleration is g times sine of theta. Okay, now remember that the tangential acceleration is dv dt, so dv dt is g sine theta. And I'm going to multiply both sides by v, so I have v times dv dt is equal to v times g times sine of theta. Now, consider that this here is the curve, and at a certain point, I'm going to take ds to be the element of length of the curve. So notice that v is equal to ds dt, where ds is equal to the square root of dx squared plus dy squared. Okay, another way to express it is to realize that this angle here is theta, so ds is equal to sine of theta times dy. So we have v times dv dt is equal to v, which as I said is ds dt, times g sine of theta. The t's cancel out, so we obtain v dv is equal to g times sine of theta ds. Now notice that, as I said before, sine of theta ds is equal to dy. So we have v dv is equal to g dy, and if we integrate on both sides from y equals 0 to y equals h, and from v equals 0 to v equals v, we have v squared over 2 is equal to g times h. So this means that v is equal to the square root of 2gh, which concludes our exercise.